So, dear students, today we are going to see about how we are going to implement the univariate linear regression, in which we are going to see about the simple linear regression and the multivariate linear regression and then logistic regression. So this is how we are going to see. So before going for the code, first we will see the theory part so that it will be very useful for you. Then you can make the code, right? So linear regression. So as you know, in the linear regression, you have a plane in which you will have that linear regression. You will have like a line equation in which we are going to classify the model, right? So linear regression mainly it makes the prediction for the continuous real or numerical variables. Say, for example, if you are having sales, salary, age, product price, etc. Okay, so we can have it as like all, we can uh, tell it as like a numerical value, right? So numerical value we will take, and it is a supervised technique, right? As we know, we have a training sample and we are going to use it, and then we will whenever a new data comes, we are going to classify it whether it belongs to one category or the another category. So that's why we can say it is a supervised technique. And as I told you, you have the types of linear regression. One is a simple linear regression and multiple linear regression. So whenever we see the data set, when we go for only one independent variable, based upon that we are going to have one dependent variable. So column, if you are having means, then we can say it is a simple linear regression. And if you have a multiple independent features, okay, so with that we are going to identify one dependent target. So then we can say it as like a multiple linear regression. More than one feature if you are having, or more than one columns, okay, independent columns if you have, and you will have only one target column based upon that, and it is a dependent one, we can say it is a multiple linear regression. Let us see with some examples so that easily you will understand the concept. So for the linear regression, as we know, that we are going to have like a line equation we have to calculate. That means in a linear relationship between a dependent y and one or more independent y variable. So we can say that that is called actually the linear regression. As we say, it is a simple, and see the different types, multiple. You can see that if it is one means it is simple, and if it is more than one means we can say it is like a multiple linear regression. So since linear regression shows a linear relationship, which means it finds how the value of the dependent variable is changing according to the value of the independent variable. So based upon the value of the independent variable, according to that it will change. For example, if you are finding the height and weight, year of experience and salary, driving speed and mileage. Okay, so all these things we can say it as like a it's a numerical value, right? Numerical value. You can see that year of experience. Okay, based upon that, the salary can change. Okay, so depend upon the driving speed. Based upon that, the mileage may change. Depend upon the height, the weight may change. Likewise, so if one which dependent with the other. Okay, so that is how we are going to tell about the independent and dependent. Okay, so when you see about the different types of regression, you can see here all these dots, we will call it as like a data points. So that only we will see it in the data set. So what are the values we are having, all that thing we have to be plotted between the x and y plane. And then we are going to form the linear regression. That means you are going to have a straight line, y equal to mx plus c, so where m is a slope and y is an how we are going to find the dependent variable based upon the independent variable, that is x and y, we are going to find out, right? Okay, so we can see here this is like uh, the line what we are forming. It is like an Okay, so we are having the predicted value and the actual value, and between this difference, we can say it as like a error. So how much the error point, which is lesser, then we can see that the plotted line, which is the best line fit. Okay, so that is how we are going to see the regression line. Okay, so that is how we are going to find out. So that's why we are having this y equal to b naught plus v1 into x1. So we can say this y is a dependent variable, and then this x, we can say it as like an independent variable. Okay, so we have to okay, keep on changing the value of it, and based upon that, the y value, dependent value also will change based upon the different value of x. Okay, so that is how we are going to find out for the line equation. We are going to substitute for it. Okay, so when what is the difference between the different correlations? Okay, so we will call it as like a positive correlation. That means okay, so one it increases, okay, the other also will increases. Okay, but a negative correlation means one it is increases, the other will decreases. Okay, so then we can say that it is a negative correlation. What about the no correlation? Okay, so that means it is like we increase the value of x, output variable y will be always flat and have the same value. Okay, so that is how we will tell about it. Okay, so when we have a variable x and y, if we compare with that, the positive correlation always we will say that when it increases, the output variable also is increases. Okay, but in negative, we will say that when x is increases, so that is the time the y is decreases. That's why you can see the plane. Okay, the line equation, it is in the opposite direction. So that means it is initially, okay, if how much it increases, we can say that the value of the thing, okay, will be decreasing. Okay, so in no correlation, you can see it is like uh, horizontal line. Okay, so horizontal line, so we can see that the output variable y will be completely flat and have the same value. Okay, so this is how we will just say that. Okay, so how you can find the best fit? Okay, so how you can find the best fit when you see here? Mm, okay, so we can see how we can see the best fit, right? Okay, once again. Okay. Okay. So how we are going to find the best fit line means, as I told you, the error between the predicted value and the actual value should be minimized. Okay, so that is how we have to say that this is the best line fit. Okay, if it is a least error means, okay, then we can say it is the best line fit. Okay, so this is how we are going to substitute the value here, and then we will find the best line fit. Okay, and the next is okay. So mainly we will see the best line fit will be like a least error. Okay, so that is how we will tell about it. Okay, okay. So this is like between the experience and salary. If you want to just measure, you can see that the year of experience versus salary. If you want to just calculate, you can see that if the experience increases, automatically the salary also will be increasing. Okay, so that is how we will talk here. The year of experience, when it increases, automatically the salary also increases. Okay, so This is how we can see that the salary which is dependent on the year of experience. Got my point? So we can say salary is a dependent and then years of experience is an independent. Okay, so this is the data set, and based upon the this independent okay value, the automatically the target or the dependent column, okay, you can see the drastic growth of salaries, okay, based upon the year of thing. Okay, so how we will calculate using the linear regression? When we see here for the initial state, you will have B naught will be like no experience, right? So that is the time B naught will have no experience. So that is the time actual okay salary you will get it. Okay, so salary initially it will be like a 30K if you are not having any experience at all. So if we want to add some more, okay, years to it, that means 1 year. If you just add an experience, so that is the time the 10K which will be added. So we can say that B naught is like a constant in which 10K which is added. So automatically 30K plus for 10K. So now it will be 40K after 1 year experience. Got my point? So this is how we will just add, okay, for the particular case study. Okay, so here in this case study, we are just finding out based upon the year of experiences, the salary also, which is increases. Okay, so this is how we will plot the value. And we can see that here yi, okay, this is the actual value, and yi cap, it is a predicted value. Okay, so we are having the predicted value, that is the line we have drawn, and this is the actual value, the data point, okay, according to the data set we have plotted, and the distance between the actual value and the predicted value, we will call it as like an error. Okay, so that only we are calculating, and it should be minimal. Okay, when we say the error is minimal, then we can say it is a best line fit. Okay, so that only we are trying to say here. And then we are finding the regression line, okay, in which y, which is target, and which is equal to a naught plus a1 into x. We have already seen, right? X is the input data set, okay, the value what we are going to substitute one after another, right? Okay, so in which A1 and A naught, how we are calculating? So here X bar, which means we can say it is a mean value, and Xi is the what value we are just actually the actual data point. Okay, so Xi is the actual data point, and Yi based upon the Xi we are going to calculate it. Okay, and then this X bar and Y bar are the mean value. Okay, so we have to put summation I equal to 1 to n, and we have to subtract the value with the mean. Okay, the actual value with the mean, right? So that is how we are putting in the numerator, and then we are going to find the square value of the okay, so the actual value minus the mean value. Okay, so cap means we will say it is like a predicted, but here bar means we will say it as like a mean value of x. Okay, so in how we can put it in the code. Okay, so there we will call it as like x of mean. Okay, that is NP. So that is the okay numpy dot mean of x, and numpy package name dot mean of y. Okay, so this is how we are going to use the function name. Okay, and then we are going to print the value of x mean and y mean. Okay, with the particular okay uh, like okay, so string, with the string we are going to print. Okay, so that means mean for year experience we will calculate based upon the x mean and y mean we are calculating from the data set. Okay, so this is how we are calculating, and we are just substituting the value of x bar and y bar for each and every input value and the target value, and we will get the value of a1 and a naught, and we will just substitute. Okay, and then coming here we will calculate the a1 again, and a naught actually already we did. How we are going to put it in the formula? We will use it as like a sum of summation, right? Xi minus mean of x into yi minus mean of y. Okay, so that is the y x bar, and this is the y bar, and then we have the original initial value minus mean of x, that is x bar the whole square. This is the denominator, right? Okay, so how we are going to give it in the code? We have to initialize as 0 and 0 because it is a summation, right? So we are going to use the for loop in which the len of x we are going to give, and then we are going to give the numerator as this is the value, right? Like as numerator which is equal to numerator plus. Initially, we are making it as 0 for each and every value of x and y we are going to calculate. With the mean will be the same, but xi value will change from. Okay, so likewise, we are going to find out for numerator and denominator, and we will calculate the a1, right? So for similarly for a naught also we found out, and just substitute to it. Okay, so you will get a1 and the a1, and then we will find out the y predict. Okay, so y pred, that is the predicted value of y we will calculate after we calculating the a naught and a1. Okay, so this is how we will put it in the code, just to know the idea, okay, behind how we are calculating the predicted outputs. Okay, so that only, that's why I am just giving this particular theory part so that you will clearly understand when you are making the code at the back end. Okay, so you have to know all these functionalities which is happening. Anyhow, you will learn in the theory. So that's why I'm just going little fast. Okay, so that you will understand when you are making the code. Okay, so how we will calculate the performance? So three category. One is R squared method. Okay, so we will calculate as like R squared. That is 1 minus SSR by SST. Okay, so SSR, that is the sum of squared errors. Okay, sum of squared errors. How we are calculating, that is the sigma of y actual minus y predicted. Actual value minus predicted value. Okay, to the whole square. Summation we are going to find out. And similarly for here also divided by SST. How we are calculating is y actual minus y mean, the whole square. So completely we are using the square here. So that is R squared. That is one category of finding the performance. And the second one is mean square error. Okay, so here we are not going to have it as like separate SSR and SST, but here we are going to have like a mean square error. How we are going to calculate the performance means 1 by n, that is the total number of value, sigma of y minus y cap. Okay, y cap is like as you know, it is a predicted, and y is the every value, right? The square of the difference between the, this is the actual and this is one is the predicted. Okay, the whole square. Okay, so this is how we are going to calculate the mean square error. Okay, that is another one. And then root mean square. Okay, here. So that is the another way we are going to calculate the performance. Here also we are going to use the sigma I equal to 1 to n, and then here also the total number of samples, and into we can put anywhere. Okay, because we are going to use only the square, right? Either yi minus yi bar, okay, cap we can put, or yi cap minus yi, because we are going to use the square. That's why we have given in the other direction. Here we have put a y cap, right? And then here we are putting a yi cap here. Okay, anyhow we are going to have the in difference, and when we make square it will become a positive value, right? So that's why we are using this root mean square error. We are calculating by means of yi cap and yi value, right? Okay, and then mean absolute value. So here we are not going to have any square, but we are going to have only the positive value, so we are using this absolute. Okay, absolute error. So mean absolute error, that is an another performance. We are going to have total number of samples, data points, and then actual output value, and then this is a predicted output value, and we are going to have the absolute. So we will get only the positive value, right? So this is an another way of finding the performance. All these things we are going to use to find the performance for the simple linear regression. Now going for the multiple linear regression. Okay, so as you know, the multiple linear regression, as I told, you will have more than, okay, one independent variable. So that's why we are putting that y equal to b naught plus b1 into x1, and then plus b2 into x2 up to bn xn. So it can be like two or more, okay, independent variables or independent okay, so columns you will have in the data set. So that's why we are telling it as like a multiple linear regression. Okay, so that is the difference from the simple linear regression. Okay, so coming to the multiple linear regression, here we are going to form a dummy variable. For example, Okay, so the profit and the spend, how much is spent for R&D and admin and marketing, and then we are going to have the state. Okay, so this particular state which has spending this much. Okay, so when we are having such thing, how we are going to use a dummy variable? See here, we are having New York, so we can make New York as one. So here, what are the category you have? One is New York and the another one is California. So this one we are going to make it as a numerical value. How to make it? See here, we have to change the thing. So instead of putting state, we can put two category as New York and California. Got my point? This is how any number of category we can make it all it as like a column name, and then we can substitute the value which is actually for that particular row. See here, New York is the answer. So I have to put one here. So California, no California, so zero. For the second row, it is California. So for California, I'm putting one. The other thing is New York, that is zero. Got my point? So this is how I can just change the categorical value into the numerical value format. Got my point? And then we can say this is the dummy variable and we can remove it. Okay, so that is also we can use it. Okay, so in this itself, we can find out which are all the ones are New York and which are all the zeros are California. Like that, we can take it at the end. Got it? So this is how we can change the dummy variable, right? Okay. So multiple linear regression, likewise, all the things which are numerical and but this state is not a numerical, it's a categorical. So we are changing it into a dummy variable, and for each and every variable we are going to substitute. Instead of state, we are going to give New York and California. We are going to give the value for it. Okay, B4 and B5, in which we are going to have the dummy variable here and all x1, x2, x3. Instead of putting x4 and x5, we are putting dummy variable d1 and d2. Okay, so now we have to remove this dummy variable. Okay, as I told you in the previous example, right? In the example, this one have to be removed because with this value itself, we can find out which are all the New York that is +1 and then which are all the California we are making it as zero. Got it? Likewise, we can just substitute the value and we can remove the dummy variable, right? Hello, always omit one dummy variable whenever we are going to use, right? Okay, so this is how we can just do it. Okay, so while we build a model, okay, so in the multiple, okay, how we are going to do it. So here some of the example all in or backward elimination and forward selection, bidirectional elimination and score comparison. Okay, so these are some of the example. If it is all in means, as you know, it's a prior knowledge. Okay, or we have to use or. Okay, so either this or that. Okay, so all we have to consider that is all in. Okay, when we go for forward selection, as you know, okay, you will have the threshold. See, for example, if you are just fixing the threshold as a okay, so 0.05. Okay, so that means okay, we are going to have the value which is greater than okay, 0.05 or less than 0.05. We are going to consider either if it is less than 0.05, the data point ranges means we are going to make it as 0. If it is greater than 0.05 means we are going to make the value as 1. Got my point? So that's why we are going to make the threshold always. Okay. And then we are going to calculate that which belongs to the which category. See, this is how we will start. In backward elimination means always we will see that one after another, whichever things which is less than 0.05. Okay, we have to include one after another. Okay, so that is how we will go for backward elimination. But coming to the okay uh, forward elimination, so we can see here forward selection means whenever the value which is greater than, okay, which is greater than the threshold value. Okay, so that is the time what we are going to do is keep this variable and fit all possible models with one extra predictor added to the ones. Okay, so you already have. So whenever the new things it comes, we are going to add, okay, across it. So that is how we are going to do for the forward selection. Okay, but for the backward selection, okay, what we are going to do is, okay, so whenever we are going to find out with the with if the p which is greater than SL, okay, the value which is make it like that. So what we are going to do is we have to remove one after another. That is called backward elimination. Okay, forward elimination means to the down we are adding one after another which is less than 0.05, but backward elimination means already okay, it will be there, right? So we have to remove one after another if it is greater than 0.05. Okay, but coming to the next, that is bidirectional elimination, in which both the thing will happen. One side to the less than 0.05. Okay, so that is the time we have to add one after another, and whichever which is greater than 0.05, right? So that is the threshold value. So that is the time we have to add. Okay, so there we are going to remove it. Okay, whenever which is greater than 0.05, right? Both the thing we are going to do it. Okay, so this is called the bidirectional elimination. Okay, so these are some of the truth we are going to see in multiple linear regression. And coming to the next, that is logistic regression. So name is only regression, but it is actually the classification technique. Okay, so how we are going to use, instead of using the line, we are going to have the S curve, and how we are going to do the logistic regression. Okay, so here also we can see that if it is either yes or no, or 0 or 1, or true or false. Okay, but instead of giving the exact value as 0 and 1, it gives the probabilistic value which lie between the 0 and 1. Okay, so that is how we are going to express here. Okay, the outcome must be either the categorical or the discrete value. Okay, so mainly the logistic regression, it predicts the output of the categorical dependent variable. Okay, so mainly it is similar to the linear regression, except only one thing, how they are used. Okay, so mainly this linear regression which is used for solving the regression problem, whereas logistic regression is used for solving the classification problem. That is the main difference. Okay, so here classification problem, but we are naming it as regression. Okay, we should not confuse with it. Okay, because regression is one category and classification is another category, but logistic regression we will call it as like a classification only. Okay, so here instead of fitting a regression line, we fit a S-shaped logistic function which predicts two maximum values, 0 or 1. Okay, so here to maximum data points we can okay, plot to it. So when you compare with the normal thing and S curve, easily you can find out how much we can improve the performance. Okay, see for example here, we can see that 0.50, which are all the things, the value data point which is above than 0.50, we can just put it into 1. Okay, whichever things which is less than zero point 0.5, we will put it as like 0. Got it? So we got a range of 0.90. So it is above than 0.50. So we will say it is going to the target as 1. Okay. And here 0.29, which is less than 0.50. So we will, okay, so we will round off to 0. Got it? So this is how we will actually do in this um, probabilistic. Okay. So logistic regression. Okay. So that is the thing we are going to do here, S-shaped. Okay, so at last you will get in this shape of graph. Okay, so when you see here in the linear regression, okay, so you can see that the data point is not covering much, but when we go for S-shape, we can see that more data points which fits. Okay, so for example, if you are seeing here, you can see that it cannot touch many data points. But when you see here, you can touch many data points whenever the like multiple data points on the same plane. Okay, when we go for yes, we can have many data points intersection, right? So that is how we are just comparing with the linear regression and the logistic regression. It gives more accurate value compared with that. Okay, say for example, if a okay, person which is greater than 75 kg, we can say he is obese. Okay, and which is less than 75 means not OBC. If we are going to find out using the line, okay, linear regression, so that is the time it is giving the value, okay, so which is giving the value for 75 kg is less than zero point 0.5. So we are saying that it is not OBC, but it is a wrong answer. Got my point? So when we go for the sigmoid, we can see here it is like as if it is a S-shaped curve. So we can see that 75, which is more than okay, zero point 0.5. So it leads to 1. So we can say greater than 75 is OBC. Got it? So this gives an accurate result compared with the linear regression. That is how we are going to say, because the error rate is less, okay, compared with the linear regression here, because most of the data points which touches the S-shaped curve, so it gives a better result than the linear regression. Okay, so that is how we are just comparing with that. Okay, so when we have the weight, okay, wn minus 1 up to, okay, so if we are having like this, okay, so we can see that when we pass to the sigmoid curve, so we are using w power t of x plus b. Instead of using m, we are using the transpose weight. Got it? Transpose of the weight, that is w of power t of x plus b. Okay, so this is actually we are passing for the sigmoid curve. Okay, normally in the other we are just using the x naught, and okay, we are using it, and then b naught and b1 we have used, right? Instead of going for b naught and b1, here we are using the transposed weight. Okay, so like that we have to substitute for it to find the okay, sigmoid curve. Okay, so when we look at the cost function, initially the point will be here and then local minima, and coming to the global minima which has a less error. Okay, so that will be the final output. This is how we are going to find the cost function from the initial point to the global minima, right? So I think this theory is enough to do the linear regression, multiple regression to implement, and the logistic regression. Okay, so you can easily make the code. I hope you got some knowledge about the implementation of the linear and logistic regression. Okay, so let us see the code in the next video so that you will get the clear picture over it. Okay, thank you.